All right, moving on into trigonometry, what we're going to try to do is take all of the information we learned about triangles and apply it to the XY coordinate grid, and you'll see what I mean by that. Okay, so this is on topic 5, measuring rotation. So the first thing to do is how do we place an angle into the XY coordinate grid? So notice, take a look at this graph I got right here, and we're going to have the the normal x-axis right here, of course the horizontal axis, and the y-axis right here, the typical normal y-axis, right? Now we're going to place an angle on there, and here's how we place an angle onto the axis. First off, the vertex of the angle is, of course, 0, 0. So 0, 0, the origin is the vertex of the angle. And the initial side, or the starting side of the angle, is always the positive x-axis. It's always. We never start an angle up here, or we never start an angle down here. So it's, again, it's a little bit different than bearings. Remember, bearings were in terms of a compass, not an XY coordinate grid, and we were always northeast or northwest or southeast, southwest, whatever. This is not that. This is applying it to the XY coordinate grid. Okay, so the initial side is always the positive x-axis no matter what. The terminal side is simply where we stop. Okay, so if I draw this terminal side here, I'm going to start at the initial side and I'm going to rotate until I get to that terminal side. And that angle right there is the angle that I've created, and we'll call it theta. Or you could call it whatever Greek letter you want to, or you don't even have to call it a Greek letter, you can call it whatever you want. So that is the idea of drawing an angle. Okay, now a couple other things we have to talk about is angles can go more than just the first quadrant. So we could rotate an angle all the way to here, and then we could draw the terminal side. Well, it's not too pretty, but we could draw the terminal side there. So that angle would obviously be an obtuse angle, would be bigger than 90 degrees, and that would be angle, maybe alpha. Okay, we could also have angles that go continuously. Okay, they go all the way around a full circle, and then they keep going. That could be an angle as well. Okay, that would be a really big angle. So that angle would be a full 360 degrees rotation around, and then it would be another 90, another 180, another 90, a total of 180, and then even some more. So the idea that I'm trying to get here is that an angle, okay, angles have a domain of negative infinity to infinity. Okay, angles can really be any value. They can take on any value they want. So once again, I can just keep going around the circle. So an angle of 1,000 degrees seems so crazy, but an angle of 1,000 degrees would just be repeatedly going around and around and around and around. Likewise, we could also have negative angles. Negative angles would simply be starting on the same initial side. Remember, the initial side never changes, but it'd be going in the negative direction. So we'd start going down. So if we drew this angle right here, we could have a negative angle right there that goes down to get it. So positive angles go in a counterclockwise rotation. Negative angles simply go go clockwise. So positive angles go in a counterclockwise rotation, counterclockwise, and negative angles simply go in a clockwise rotation. Okay, so this is what I'm trying to show you, that the domain here of angles is really all values, negative infinity, positive infinity. Okay, here's some simple examples. Just want to show you a couple pictures of some angles. So for example, 45 degrees would be always starting. You always start here on the positive x-axis, and then we rotate up 45 degrees. So that'd be right in between 0 and 90 there, would be the 45 degrees. Look at 90 degrees, you almost can't see it. That's because the initial side was right here, and the terminal side was right here. So that would be a perfect 90 degrees. So that would fall right onto the quadrant there. Okay. Also, here would be 225 degrees, for example. So 225 degrees would be going 90, 180, and then a little bit more for 225 degrees. Okay. Here's negative 45. Notice the direction of the arrow really matters here. Now I'm going clockwise. I'm going down. So that'd be negative 45 degrees. Okay. Here we go. Here's what we have. These are called the quadrantal angles. Let me write that out. QU, and I gotta look down how to spell this. Quadrantal, I think that's a word, pretty sure. Quadrantal angles, okay? These are the angles that make up the full quadrant, okay? They end on the x or y axis. So 0 degrees would be right here, okay? So you don't go anywhere, 0 degrees. 90-degree angle would go straight up to the 90 degrees. 180 would go all the way around to 180 degrees. And 270 would go all the way. So 90, 90, another 90 for the 270. We also have 360 degrees as a quadrantal angle. And 360 degrees would be going all the way back to the initial side. But again, that would be the same as 0. So 0 degrees and the 360 degrees would technically be the exact same ending place, that exact same terminal side. So this brings us up into talking about angles that are what we classify as coterminals. Okay, coterminal angles. Let me just write down a definition here. Angles that share a terminal side. Now remember, every angle, no matter what, shares the initial side, because every angle, no matter what, starts on the positive x-axis. So angles that share a terminal side. Okay, so let's talk about 30 degrees, for example. So here's a beautiful picture of 30 degrees. Give me another angle that would end at 30 degrees as well. Well, I could go negative to get there. So what angle would that be? Well, you could think of as the whole thing as 360. So if I do 90, I'm sorry, not 90. If I do 360, take away that 30 degrees, I have 330 degrees, but it would be negative. So this angle right here, I'll call it beta, would be negative 330 degrees. Again, it's the same terminal side. So it has the same terminal side, so it just ends there, but I went in the negative direction to go get it. Also, I could have another coterminal angle. I could go like this to get there. I could go all the way around 360 degrees and then another 30 degrees, and I would end at that same terminal side. So that would be 360 degrees plus 30 degrees, or 390 degrees. Okay, so basically, to find a coterminal angle, start with the angle you're given, alpha, and you could actually add or subtract 360 degrees n. Now the n represents the fact that you can continue to add 360. So if I'm at 30 degrees, I can add 360, add 360, add 360 as many times as I want. That's the n, representing that you could do it once, twice, 3 times, 4 times, 5 times, 6 times, 7 times. You can do as many times as you want. And you would keep ending at that same side. So if I start with 30 degrees, so let me show you on my calculator here. If I start with 30 degrees and I add 360, okay, I get a coterminal angle, 390. I can add another 360, get another coterminal angle. And I can actually continue to add 360 over and over again and continue to get more and more coterminal angles. Likewise, I could start at 30 degrees and just go backwards and subtract 360 to get a negative coterminal angle. So you would just go the other direction. And again, I could subtract another 360 degrees. And go again. So that'd be another coterminal angle, another one, another one, another one, another one, another one. So coterminal angles just constantly repeat themselves. There's an unlimited amount of them. So whatever angle you find, just keep adding or subtracting 360 as many times as you want. And I kind of drew another picture here to show you the 390 degrees. I know it doesn't show it extremely well, but it would be the full circle, 360 degrees, plus 30 more for the 390. So that's kind of the idea of coterminal angles. So these coterminal angles are just angles that repeat themselves over and over again. Okay. The key idea is that they have the same coterminal side. All right. So here's a quick example. Which angles are coterminal to 45 degrees? So you'd start off with 45 degrees, and you would add or subtract 360 as many times as you want. So again, if I want to create a list of coterminal angles with 45, I could start with 45 degrees and add 360 and add 405. That would be one coterminal angle. Let me write that down, 405. I could continue to add 360 again and again and again and again. So again and again and again and again to get more and more and more and more and more coterminal angles with 45 degrees. Or likewise, I could go with 45 degrees minus 360 and get a negative coterminal angle, negative 315. And I can continue to subtract 360 degrees to get more and more and more and more and more negative coterminal angles. All right, so that's the idea, is that there's plenty of coterminal angles out there. All I got to do is add or subtract 360. All right, let's apply this to the next topic, topic 6, applying trig functions to angles of rotation. All right, now this is actually pretty cool. Now think about it. If I take an angle and start rotating it, I'm going to create what? A circle, okay? And that circle size is based on its radius. Obviously, a small radius would create a small circle. Big radius would create a real big circle. And this is a particular circle I showed you right here. I'm just going to be generic with it and call it radius r. So as you move around that circle, you stop at a certain point. So let's stop at this point right here. And of course, that point is an x comma y. It's a point in the coordinate plane. So where I stop is going to create an angle. So here's the angle theta at which I stopped. Right there. It'd be a positive angle here in quadrant 1. This would be quadrant 1. Okay? Now, when I stop at that angle, I could go to that point and I could drop a line straight down and a line straight across to create a right triangle. Interesting. We've been learning about right triangles a lot lately. So we create this right triangle, and based on angle theta, y is the opposite, x is the adjacent, and r is the radius. The radius, but r is the hypotenuse in terms of the right triangle. So I could actually identify sine of theta as the opposite side y divided by the hypotenuse r. I can do the same with cosine. Cosine of that angle would be the adjacent side x divided by the radius r. I can go again. Tangent of that angle would be the opposite side y divided by the adjacent side x. And I can continue this. Now, it all depends on where I stop. Okay. Now, if I would have stopped right here, for example, then I would have a smaller angle, obviously. So, smaller angle. This angle right here would be smaller than theta. So let's call that alpha. And again, this would stop at another x and another y, but I could draw another triangle as well, right? So there's another 90-degree triangle. And again, my adjacent side would be x, my hypotenuse side would be y. Or my opposite side would be y, and the hypotenuse would be r, of course. So again, sine of that angle would be y over r, cosine would be x over r, and tangent would be y over x. And you also, don't forget, you have their reciprocal functions. That would be cosecant. Cosecant of theta would simply be r over y. Secant of theta would be r over x. And tangent of theta would be x over y. Whoa. Sorry, take that back. Not tangent. Cotangent of theta would be x over y. So anyway, that's how this stuff applies, the trig functions, to these actual angles of rotation. So I wanted to kind of talk about some different things here based on these triangles real quick. I want to prove a couple of things to you. So let's start off with, for example, let's see here. Let's talk about this point right here. So let's say that here's our starting angle, right? We always start in that positive x-axis. Let's say that we rotate all the way to this angle right here. So that's a pretty big angle right there. That would be theta. Okay, now where we stop, once again, is an x value, comma, a y value. Okay, so if I drop this straight down and come straight over here, I create this 90-degree angle where the height of that would be y, and the side down here, the horizontal length, would be the x. Now, you may be saying, wait a minute, I see that triangle, and this is the angle I'm focused on right here. Well, you're right. That angle is obviously important, but it doesn't affect the trig functions, believe it or not. Sine of theta is still y over r, where r is, of course, the radius. Cosine of theta is still x over r, and tangent of theta is still y over x. Those things don't change just because we're talking about this particular other angle here. And I guess I kind of want to try to prove that to you. Now, the only thing that's going to change is, think about it, in this quadrant 2 right here, the x's are going to be negative. So that means cosine would be negative, and sine, the y's are still positive, so that wouldn't change sign. And tangent actually is division of y divided by x. So if x was negative, then tangent would be negative as well. So I kind of wanted to show you this with an example. Let's pretend that the angle I'm talking about right there is 150 degrees. 150 degrees, okay? So let's just say that, here, let's actually draw 150 degrees. So I'll draw it on this one right here. So here's my angle, 150 degrees. Let's see, that would be 90. And then another 60 degrees, right? If you think about it. So it'd be somewhere right, I don't know, somewhere right around here. I'm just trying to get an idea of where 150 degrees would be. So it'd be 90 degrees and then another 60 to make up for the extra over here. So anyway, the key thing I'm trying to find is with this leftover angle. So we're talking about this triangle right here, right? Here's this right triangle. And this angle in that right triangle would obviously be 30 degrees because the whole thing is 180. That pink part right there is 150. So that remaining part down there would be 30 degrees. So here's what I want to show you guys using the calculator, okay? Now, if I look at that green triangle down there and I think y, right? I think y is the opposite, x is the adjacent, r is the hypotenuse, okay? And I'm thinking about sine. Sine of 30 degrees would be 0.5. Believe it or not, 0.5, 1/2, 0.5. So sine of 30 degrees is 0.5. So if I take y, divide it by r, I better get 0.5. I don't even know what y and r are, but I'm going to get 0.5. Now, notice if I do sine of 150 degrees, the peak angle, I also get 0.5. So what I'm trying to prove to you is that this green angle is 30, this pink angle is 150, but it's still going to result in the same sine value. Now let's do cosine. Cosine of 30 degrees is going to be 0.866. Okay, so x divided by r, cosine, I don't even know what x and y are, but if I take x divided by r, I'm going to get 0.866 at 30 degrees. And if I do cosine of 150 degrees, notice what happens. I get the exact same value, 0.66, but I get negative. And all that negative means is because I'm in quadrant 2. And in quadrant 2, x's are negative. So when I do cosine of 150, I better get a negative value for cosine, since cosine is a combination of x divided by r, but x is negative in quadrant 2. So that should hopefully make a lot of sense to you. We could also do tangent of 30 degrees. 0.577. So that means that y divided by x, I don't even know what y and x are, but if I divide them, I'm going to get 0.577 apparently. And if I do tangent of 150, I'm going to get the exact same value, but negative. And that's because tangent is a combination of y divided by x. But if x is negative, I'm going to get negative 0.577. Okay? So hopefully that makes plenty of sense to you. I really hope it does. I wanted to show you another example up here as well. Here's another example I'm showing of theta, an angle that ends in the second quadrant here. Okay, this is quadrant 2, and in quadrant 2, x's are negative, y's are positive. Okay, so here I create this triangle. Right, let's just say I end at the exact point -3, 4. Okay, and you don't have to worry about finding this angle right here. A lot of people think they do. Obviously, it would be 180 minus theta. Sorry, that's kind of messy there, but you don't have to find it. Watch. It's so easy. Sine of theta, even though theta is this angle over here, sine of theta is going to be 4/5. And in quadrant 2, y is positive 4. R is our distance. R is a radius. Radius is a distance, so that's always positive no matter what quadrant you're in. So I get 4/5. Cosine of theta. If you just look at the triangle, you're going to say 3/4. Right? Adjacent 3, hypotenuse 5. Whoa. My fault. Adjacent 3, hypotenuse 5. But you have to put a negative on it, right? It's got to be negative because in quadrant 2, x's are negative. In quadrant 2, x's are negative. So you need to make sure that would be negative 3/5 because you're in quadrant 2. That's where the difference falls. Tangent, again, if you're just looking at the triangle alone, tangent would be 4/3. But I can't just look at the triangle alone. I have to consider what quadrant I'm ending in, or the terminal side is in, and that would be a negative x value. So that would be negative 4/3. Okay, so that should be pretty easy. Okay, now let me do another example down here in this bottom, or I'm sorry, in this top right picture. What if I ended at this angle right here? Okay, so what if I start out this initial side right here? Hopefully you can see this pretty blue color, and I come all the way down to there. There's my angle theta. Okay, there's theta. Well, this is still a point x comma y. Okay, my triangle would be the triangle drawn straight to the x-axis. So there would be my triangle right here. Beautiful triangle, right? And you may say, wait a minute, theta, I understand this is y. I understand this is x. I understand this is the radius r. But this is the angle, right? This is the angle right here. I know, but it doesn't matter as long as you apply that x and y in quadrant 3 are both negative. In quadrant 3, x and y are both negative. So sine would be y over r still, but it would be negative because you're in quadrant 3. Y's are negative. Cosine would still be x over r. That wouldn't change. So cosine of theta is still x over r, but it would be negative because x's are negative in that quadrant. Tangent would actually be positive because tangent is y divided by x, and if both of them are negative, then two negatives are going to make a positive. So hopefully that makes sense to you. So this general rule of sine of theta is y over r, cosine of theta is x over r, tangent of theta is y over x applies, and it always will work as long as you consider what quadrant you're in, and x's and y's being, of course, positive or negative. So that's how we're going to kind of combine circles and rotating into the trig functions, and then we're going to kind of throw in the coordinate plane as well. So actually combining a whole lot of things here. We're combining the coordinate xy plane, right? We're combining circles with triangles. So it's all based on where you end. This is where I end. Let's call that alpha. Draw a triangle, and you're drawing that triangle straight to the x-axis. So there's my triangle right there, and I know that this is the y value, this is the x value, and there's the r radius. So the x and y could be positive or negative depending what quadrant you end up in, and r will always be positive because radius is simply a distance, and distance is always positive. All right? So hopefully that's a good kind of introductory lesson for you on how we're going to turn angles and rotating into this idea of quadrants and trig functions and the coordinate graph, the coordinate grid. All right. So see you guys on Wednesday. Actually, have a good weekend, and talk to you later.